All right, thanks so much. Thank you for the introduction and the invitation. It's a pleasure to be here. This is my first in-person talk since the end, so thank you very much. Yeah. I should say that comes with the downside. This is the only Beamer talk I've given not via Zoom. So if there's some unanticipated transcription failure, then I apologize in advance for that. I want to talk about periods in the world of algebraic varieties. And for the most part, this is going to be a pretty down-to-earth talk where I want to sort of survey a bunch of ideas, especially some recent progress, because these are pretty sort of fundamental objects in algebraic geometry and in sort of complex geometry generally. So let's start with a smooth projective complex variety. And by that, I mean very simply just a complex manifold X, which arises inside of complex projective space as a set of solutions to some polynomial equations. Yeah. So as a recurring example, very simple example, I want to sort of take with us the example of an elliptic curve. So fix some parameter lambda. It should not be 0 or 1 for reasons I'm about to say. And let U inside of the complex plane be solutions to this particular cubic equation. Okay? So lambda should not be 0 or 1 in order to make this a smooth algebraic curve. Of course, it's non-compact, so it's useful to compactify it. So we complete it by closing it up in the projective compactification of the complex plane. And we do that by forming the associated homogeneous. Okay, so this is now a compact projective curve inside of projective space. And if you haven't seen this before, this is the elliptic curve. So a fundamental invariant of any sort of complex manifold is its cohomology groups. And within algebraic geometry, there's at least 3 ways to think of these cohomology groups. We can think of them topologically, we can think of them differential geometrically, we can think of them algebraically. So the topological avatar is probably the simplest, one we're probably all familiar with. We think of this cohomology group as just complex forms on singular occasions. This is important because it in fact gives a natural integral structure to this complex vector space, namely the forms that are integer valued on singular occasions. So in our example, we know that this elliptic curve, or maybe we don't know, but it turns out that this elliptic curve is a 2-dimensional torus. So its first homology is generated by 2 loops going around sort of 2 holes of the torus. And the cohomology, a basis for the cohomology is obtained by just taking the dual bases of those 2 loops. Now, differential geometrically, we can extract a bit more information. So the key starting point is the de Rham isomorphism, namely integration against a chain, against a cycle, allows us to identify the singular cohomology groups with closed complex valued smooth forms modulo exact complex valued smooth forms. In fact, we can do slightly better because projective space carries a Fubini study metric, which is a Kähler metric, and I can restrict that to X, and thereby I can talk about harmonic forms, harmonic classes of forms, and it turns out that each de Rham cohomology class has a unique harmonic representative. Okay, so I can think of de Rham cohomology classes as just harmonic smooth forms, harmonic with respect to the Kähler metric. And the critical reason this is important, or more specifically that we're dealing with the Kähler metric, is that for any sort of smooth form, I can break it up into its PQ pieces depending on sort of how many ways it depends holomorphically and how many ways it depends anti-holomorphically. And this gives us a decomposition of harmonic forms by taking PQ apart into the sort of harmonic pure type form, and it gives this decomposition. Okay, and moreover, this decomposition has this kind of conjugate symmetry, because if I take a harmonic form that has pure PQ type, then its complex conjugate is pure. If you haven't seen this before, let me just write it. I mean, all I'm saying is any smooth form with respect to holomorphic coordinates, let's say there's n of them, there'll be some number of dz's. There'll be some number of dz bars. Recording the number of sort of dz's and the number of dz bars. Okay, that's what I mean by it. Okay, so this structure, namely giving an integral lattice, which over C has a decomposition with this conjugate symmetry, is what's called a weight K Hodge structure on this lattice C. And it turns out we've added a lot more information to our topological invariant by also considering this decomposition. So just to go back to our example, if we take our elliptic curve, well, we know from complex analysis that this elliptic curve can be realized as the complex line modulo a lattice. And in fact, that lattice can be seen in terms of this decomposition. Okay, so in this case, if we're talking about the first chromology, there's only two decomposition pieces, the ones that have a single dz and ones that have a single dz bar. And it turns out harmonic forms are just the ones that are holomorphic or anti-holomorphic, of which there is exactly one up to scalars, namely dz, where z now being the coordinate upstairs. Dz is translation invariant, so it descends this elliptic curve, give me my unique holomorphic form, and correspondingly I have a unique anti-holomorphic form. And we can in fact recover the lattice by integrating this holomorphic form dz along all homology cycles, right? Indeed, I mean, right here, if we think of E being a quotient of sort of say this parallelogram generated by 1 and the complex number tau under translation by 1 and by tau, then the integral along this path gives us 1, and the integral along this path gives us tau. Okay, so equipped with this additional datum of this Hodge decomposition, we can nail down the elliptic curve E as a holomorphic manifold. So it carries way more information. It's in fact a complete invariant for elliptic curves. This is a general phenomenon. For instance, for any compact UIC Riemann surface, we can do a similar thing. We can look at how the Durand homology splits into harmonic forms. Once again, the harmonic forms are just the holomorphic and anti-holomorphic ones. And if we choose a basis of holomorphic forms, of which there are now G, then we can look at all the integrals we get, integrating against the now 2G generators for first homology. And we'll get some lattice inside a G-dimensional complex vector space. And the quotient is a complex torus, back to the Abelian variety, which is just the Jacobian of this curve. And it determines X, although by a slightly more roundabout way. So for the elliptic curve, we can literally recover the elliptic curve from the information of its lattice inside C by taking the quotient. Here, it's a bit trickier, but in a precise sense, the curve is still determined by its Jacobian. And likewise, this is what I was mentioning before. Turns out this happens a lot in algebraic geometry. Not all the time, but a lot. So for instance, the Hodge structure on the cohomology of an Abelian variety will completely determine it. We've essentially already seen that. You can recover the lattice by integrating holomorphic forms along all the cycles we have available to you. Slightly more mysteriously, this is true for hyperkähler manifolds and also true for Glavier manifolds. And just to throw in sort of another example of the different flavor, most complete intersections in PN are also determined by the Hodge structure on their cohomology. Okay, so this is a pretty powerful invariant. Now let's take a brief side road here into Hodge classes.
By the way, in the case of complete intersections, did you mean that you first pick the topological type and then you mean within that the algebraic?
Yeah, that's right. So I'm going to cut down by degree di hypersurfaces, and I sort of fix the degrees, and that's
Yeah,
sort of
so
the same.
you have to fix multi-degree in it.
Exactly. Yes, that's right. Yep. Okay, so Hodge classes play an important role in this story. What are they? Well, in general, if I take some sort of singular cohomology class and I ask what are its PQ decompositions, that's sort of a very transcendental question. It's not really clear what the PQ components are doing because we have to sort of first move by the Durham isomorphism to the cohomology class, so a smooth form, and then break it up into harmonic components. One thing that is true is if I take a cohomology class, which is Poincaré dual to the fundamental class of some k codimensional algebraic subvariety, then we know exactly what the PQ components are. Namely, what does it mean to be Poincaré dual? Well, it means integrating a complementary dimension form along the subvariety Z is the same as wedging up by A and then integrating. And if this omega Z is a holomorphic subvariety, so it only has dim x minus k holomorphic coordinates. So if this is anything other than type dim x minus k comma dim x minus k, this restriction will be 0. It'll either have too many DZs or too many bars. Okay. In other words, this wedge for omega that's anything other than sort of middle Hodge type will be 0, and that implies that in fact this cohomology class has to have pure Hodge. Okay. And notice that because of this conjugate symmetry, this is the only way a real class can be a pure Hodge type, right? Only if it's in middle, right? Because if it's real and it has a PQ component, it must also have a QP component. Therefore, if it only lives in one of them, then it must be. Okay, so these particular classes are special. They're called Hodge classes, so integral classes which have this pure Hodge type. And the sort of famous Hodge conjecture says that they have meaning. In other words, up to sort of rational coefficients, the Hodge classes in this Hodge structure actually come from k codimensional algebra. Okay, so finally, let's treat the sort of third avatar of the cohomology of an algebraic variety, and we have to pause for a second here because there's sort of no hope of recovering the HPQ pieces algebraically. There's many reasons for this. One of them is that sort of complex conjugation is a weird thing to find algebraically. Okay? And the fact that they have this conjugate symmetry is a little strange from that perspective. However, here's a sort of clever observation. If we, instead of the splitting, record this filtration, right? We add together all the HPQ pieces with p bigger than or equal to a fixed thing. So that gives me some filtration of the cohomology space. I can actually recover the HPQs by taking an appropriate intersection of FP with FP bar. Now, as it turns out, what can be reconstructed algebraically is the cohomology group together with this filtration, which again determines the Hodge structure. Okay, so this is best seen by an example. Let's go back to our elliptic curve, or actually a compact one surface. The way we algebraically understand Durham cohomology is in terms of closed meromorphic one forms with no residence. Okay? So if we sort of naively look at on a curve, every one form is closed. That's why it's in parentheses. But meromorphic one forms with no residues can still be integrated, and so they get well-defined sort of cohomology classes here. We mod out by exact forms. It turns out this gives me an isomorphism. And of course, meromorphic one forms are all algebraic. They're all rational forms. And moreover, the filtration in this case just has one interesting piece, namely the F1 piece, and that's exactly the holomorphic one forms, which are again algebraic. Okay, these are the algebraic, these are the rational forms that are regular in every form. We can completely recover these two case, there's a variety of ways to do this. The sort of most concrete way to understand this is kind of the higher dimensional analog of this. Basically, we can still think of Durand cohomology in terms of closed meromorphic forms where we allow poles along some ample divisor. And then this filtration F is sort of the filtration by pole order. Okay, so you can sort of see that happening here. This is where you have no pole, i.e. you're holomorphic. And then the full Durand cohomology is where you allow poles, namely our meromorph. Okay, and the key point here is that since I've constructed this algebraically, it in fact works if x is defined over Q bar. In other words, if x is defined by polynomials whose coefficients are algebraic numbers, then this gadget is a Q bar vector space and the filtration is defined. So that gives me some additional structure. Questions so far? Cool. Okay. So I want to say a few words about the growth and period conjecture, which vaguely speaking says that these three different ways of thinking about singular cohomology, if there's sort of any unexpected, how to say, interaction, well, let me just state it, and then I can sort of wax philosophical on it. So here's the statement. We can form these period integrals. Okay, so if I start with an algebraic variety x defined over Q bar, on the one hand, I can take an algebraic form, for instance, some the Durand cohomology class of some meromorphic form. And on the other hand, I can take a singular cohomology class, and I can form this integral. Okay, so this integral is secretly using this sort of very transcendental isomorphism between the singular cohomology and the algebraic cohomology. So, not surprisingly, these numbers I get are often very transcendental. Right? They can't be computed in terms of the polynomials that are cutting out x. But if there is some algebraic independence among them, there had better be a geometric reason. And that's what the period conjecture is saying. So let me give a very concrete and provable example. So let's go back to our elliptic curve, which is defined by this equation. We can, we already wrote down these integrals, and we found that we can recover this parameter tau by taking the ratio of the integrals for a basis of homology, alpha and beta. Okay, so this, as my picture indicates, is an element of the upper half plane. Okay, and we recover E as the quotient of C by the lattice generated by 1 and tau. And tau and lambda are connected by the J function. Okay, so you should think of the J function as giving you the algebraic parameter for this elliptic curve. So lambda is an algebraic parameter. Tau is this sort of complex analytic parameter that's telling you the lattice. The connection between the two is explicitly given by this formula. The J invariant as a function on the upper half plane, evaluated on tau, gives you this algebraic combination of the lattice. Okay. So indeed, the J function is in general a very transcendental function. You wouldn't expect there to be much relationship between the algebraicity of tau and the algebraicity of J. And in fact, you can nail down exactly when you do have such an accidental algebraicity. A theorem of Schneider says that tau and J of tau are both algebraic numbers if and only if tau is an imaginary quadratic number. Okay, that's the first statement. The second statement is that within the context of Hodge theory, being an imaginary quadratic is interpreted as this Hodge structure having extra Hodge classes. Okay? So the only way these tensor powers of the Hodge structure acquire more Hodge classes is if this tau is an imaginary quadratic. And by this transcendence theorem, that happens if and only if sort of J of tau and tau have some unexpected algebraic independence. And then finally, given that we know the Hodge conjecture, in the case of this elliptic curve, or elliptic curve, extra Hodge classes happen if and only if there's extra geometry. Okay, so we can actually read off the fact that these extra Hodge classes that happen if and only if there's some algebraic independence happen if and only if there are more maps than you would expect from E to itself. Okay, so in this example, what we're concluding is that most of the time, tau tau and j of tau have algebraically nothing to do with each other, and they do if and only if there's a geometric.
Could you remind me what extra Hodge classes mean when you have H1 tensor to the K?
Yeah, right. So, turns out this notion of a Hodge structure, meaning a lattice with a composition over C, is stable under taking tensor power. So if you take a tensor power, that will still have a Hodge composition. And this will therefore have a notion of Hodge class here. So the one that's most relevant here is how do I produce Hodge classes associated to a map? Well, I take the graph of that map inside E cross E, and the second tensor power of H1E shows up by the Kunitz formula in the cohomology of E cross E, and that's where you find extra Hodge classes when the parameter tau is imaginary. So, for those who have seen this before, I mean, what we're really saying is that something special happens in this context if and only if E is a CM of E. Okay, so unfortunately, this is basically as far as you can get in some sense. Period conjecture is very hard, and there's many stumbling blocks. The transcendent statements that you need are hard. The Hodge theory part is hard, and the Hodge conjecture is hard. Okay, so transcendence of numbers is particularly difficult. We can ask, what about the functional analog? And let me describe what I mean by this. What I mean is basically, what can we say about the transcendence of these functions in families? Okay, so suppose curly x to s is an algebraic map with smooth projective fibers. So in other words, algebraic family. And by a resonance theorem, because this is a smooth map, the topology is not changing fiber to fiber. Okay? So if I form the chromology groups of each fiber, they all look the same, and those assemble into a local system. Sort of differential geometric avatar of this is that the Durand cohomologies assemble into a vector bundle with a flat connection, namely the Gauss-Menin connection. In other words, I can use a local topological trivialization to propagate any section over a fiber nearby functions. And in fact, this connection, it turns out, is algebraic if we compute this Durand cohomology of the relative situation now algebraically in terms of meromorphic forms. So we can do the following. Over some, say, small ball inside the base S, we can take some flat family of K cycles. Okay. By flat, I just mean the sort of locally trivial. And I can take some algebraic cohomology class in the total space, i.e. the class of a closed meromorphic K form. And I can restrict it fiber-wise to an algebraic class in each fiber. And I can form these integrals. These are now functions from B into C. Okay? So I get some number of functions. Before I had some number of numbers I was computing. Now I have some polymorphic functions. And we can ask the natural question, what can we say about the transcendence of sort of the field generated by these numbers? Cool. Okay, so this isn't going to be so relevant right now, but it's sort of an alternate way of thinking about these numbers we're producing. And that's via the Picard-Fuchs equation. So let's go back to our example. Our example naturally forms an algebraic family if we start varying lambda. Okay, so this gives us a family of elliptic curves, a family over the complex line modulo minus 0 and 1. Okay, now we've already seen that the Durand cohomology in this relative setting can be interpreted in terms of meromorphic forms. And the F1 of it can be interpreted in terms of holomorphic forms. And we can write down a form which is holomorphic on every fiber, namely dx over y. Or perhaps classically, it's more easily recognized as dx over the square root of the product of those three numbers. Okay, so this gives us a class in the F1 part of H1 around. We can apply this Gauss-Menin connection to it. Now, thought of algebraically, this Gauss-Menin connection is very simple. It's just differentiation with respect to the parameter. If I represented as a class of a meromorphic form. So, d of this d lambda, and it's this. Okay, and we notice that this is indeed some meromorphic form with no residues. So it gives me a de Rham cohomology class. Now, the rank of this group, and this is now really a vector bundle over S, which fiber-wise gives us the ordinary de Rham cohomology. But in any case, its rank is 2, because on every fiber it's 2. So if I apply the connection again, I get 3 things in a rank 2 space. So there had better be some dependency between them. And it turns out you can compute what the dependency is, and it's this differential equation that that this particular algebraic form omega satisfies. In particular, if we now integrate this differential equation with respect to some flat section, then what we're finding is that these period functions that we define are solutions to this differential equation, which is called the recur equation associated with this family. And so we see that sort of one way to think of these functions as sort of solutions to very special algebraic differential equations, namely the ones arising as the Gauss-Lemie connection of an algebraic family. Okay, I could have started this talk, of course, by writing down an algebraic differential equation and said, well, let's study the solutions. The fact that it's coming from geometry actually means a lot about the solutions that isn't true for some random algebraic differential equation. For instance, it means that the monodromy of the solution sort of stabilizes an integral lattice, and it means that it also stabilizes sort of a harmonic metric. Well, there's a lot of interesting structures that are additionally preserved by these differential equations that come from geometry. Okay, in any case, our basic objects of study are these period integrals, which we've seen in many ways completely capture how to say, there for many interesting kinds of families, they're complete invariants for that class of variety, although it's somehow difficult to recover the variety from that invariant. Let's be a little more precise about what we mean about the transcendence properties of these functions. Okay, and this brings us to Ax-Shanuel conjecture. Okay, so let's start with a very classical conjecture that was made by Shanuel a while ago, I think in the sort of first quarter of the 20th century, which is still wide open. And it's a very simple statement. It says that if you take n random complex numbers, which are Q linearly independent, then the transcendence degree of those numbers plus their exponentials is bigger than or equal to the number of numbers n. Okay, so let's digest this for a second. So one sort of consequence of this is if I take my alpha 1 through alpha n to be algebraic numbers, then of course this part adds nothing to the transcendence degree. So it's saying the exponentials of algebraic numbers are algebraically independent. Okay, so we're recovering the Lindemann-Weierstrass theorem from this more general conjecture. On the other hand, if you plug in, let's see, if you plug in alpha 1 is equal to what do I want to take? Maybe pi I and alpha 2 to be 1. This conjecture is stating that E and pi are algebraically independent. Okay, so there's sort of some strong implications to this Shanuel conjecture, which, like I said, is still open. In fact, it has a very similar flavor to something we already used, this theorem of Schneider, which can be rephrased as saying if tau is not in the upper half, if tau in the upper half plane is not imaginary quadratic, then tau and j of tau must be algebraically independent. Okay. Sorry, they can't. That's wrong. It's not an imaginary quadratic, that they can't both be algebraic numbers. Okay, and indeed, you could sort of, conjecturally, you would expect this Shanuel conjecture to still hold if I were just replace the exponential function with the j function. So this is now not known. Same extent that the Shanuel conjecture is not known. If you take a bunch of numbers in the upper half plane, none of which are imaginary quadratic, and no two of which are isogynous, then you expect that the transcendence degree of the tau i's together with the images of the j function is at least f. Okay, so this is a statement about transcendence of numbers. This is the kind of statement that we want to sort of upgrade to a statement about transcendence of functions. Okay, so how do we do that? Well, luckily, this was already done by Axe in the 70s, who proved the following functional analog of the general conjecture. Okay, if I take holomorphic functions, f1 through fn, on a ball, which are two linearly independent modular constants, then the transcendence degree, now over C, of the field generated by those functions, together with their exponentials, is at least n plus this other term. This other term is the rank of the Jacobian matrix of those n functions. In other words, it's sort of getting at the sort of formal transcendence, like the transcendence as power series of these functions. I'll say more about that. So something I haven't said anything about, which you might have been wondering, is why are we assuming that Q linearly independent? And that's to rule out the kind of obvious algebraic dependence a bunch of functions could have with their exponentials. Notice that if these fi's are sort of Q linearly independent, well, when I exponentiate a Q linear relation, I get a monomial relation of the exponential. Okay, so that's the sort of one type of algebraic relation that these two guys could possibly have. And we want to rule that out. And this theorem is basically saying that aside from those, there can be no sort of interaction between algebraic relations between the fi's and algebraic relations between their exponentials. Now, this is the way that Axe originally phrased his theorem, but it is sometimes useful to think of it a little more geometrically. So here is an alternate formulation. Suppose we consider a complex analytic subset of the graph of the exponential in the product. Whose projection is not contained in the coset of a proper subtorus. Okay, so this condition is preventing us from having a Q linear relation among the coordinates of this group. Right? In Cn, not being Q linearly dependent is the same as not being in the coset of a proper subtorus. Then the claim is that the Zariski closure of this complex analytic set is at least as big as the dimension of U plus n. Okay, so this is, term by term recreating this inequality. The rank of the Jacobian matrix is the dimension of U. How do I go between them? Well, my functions f1 through fn are just a parameterization of U as an analytic subspace. So just take functions. If you want to take a ball inside U, and those fi's are just the coordinate functions of that ball. So dim U is the rank of the Jacobian. The Zariski closure has dimension just equal to the transcendence degree. That's what this is capturing, right? It's capturing how many algebraically independent factors we have. That's exactly the function field of the Zariski closure. And then, of course, the n term. Here's a third way to think of it. We're getting sort of increasingly geometric. So take an algebraic subvariety of this product. And suppose we take some intersection with the graph of the exponential, which has unexpected codimension. Okay, so in other words, the intersection, the codimension of the intersection in the graph is smaller than you would expect naively by just cutting down by W. Then there has to be some reason for that. And the reason is that it's contained in the coset of a proper subset. Okay? So this is the kind of statement we're after, and this is sort of a statement that lives in the world of atypical intersection theory. We're saying we have some sort of transcendental locus, namely the graph of the exponential, which sits inside some algebraic variety, namely this product. And what we're capturing here is that if I have a intersection with an algebraic variety that's unexpectedly big, then there has to be a reason. Okay. And of course, intersecting with an algebraic variety is just the same as looking at the locus inside the graph where those algebraic relations exist. Okay, so here's now a general setup in which we can ask these sorts of questions. let y be an algebraic variety, and let M check be some algebraic variety with the action of some algebraic group. I'm going to be a little vague about this for the moment, but you'll see in context what we want here. And we want to sort of think about locally liftable holomorphic maps to the quotient. Okay, so that's a lot of nonsense words. What I'm actually doing is I want to capture the data of holomorphically associating to y a point in M hat up to some monodrome. Okay. So, and that's why this quotient by Z is showing up. We want to look at associating 2 points in y, objects parameterized by M hat, modulo monodromy, which we're requiring to be in sort of the integral point. Okay, so that's a general setup. Something that it includes is sort of families of Hodge structures, as we've been talking about. So if I take X over S to be a smooth projective family of algebraic varieties, then I can take M to be just the moduli space of Hodge structures on this, the chromology above a single point. I'm just fixing that as a lattice. And I can take M hat to be the algebraic variety, which parameterizes Hodge filtrations on this fixed complex vector space. Okay, so we already saw that this set inside, in fact, as sort of a semi-algebraic open set, because the Hodge filtration determines the Hodge structure here. We know that we can then form a holomorphic map from the base of this family into this quotient, because up to monodromy, I can associate to any point a Hodge structure on this fixed lattice by just choosing some point, some path to parallel translate along to identify the cohomology group above the point S with the fixed base. Okay, so long story short, the fact that in a smooth projective variety, I can associate to any point the Hodge structure on a fiber, but that's only up to monodromy, where I can identify the fibers, gives me a map of this. This is what's called a period map. Okay, so I'm sort of skipping this is an example. Now I'm going to immediately erase this example. And so now in this general setup, which includes the example I just gave, we want to ask this sort of actionable type statement. We want to say, suppose I have an algebraic subvariety of this product. And suppose when I intersect down by what is essentially the graph of this period map, I get a component of unexpectedly big dimension. Then what must be true about this U? What is the sort of what is explaining the fact that I have this unexpectedly big intersection? Okay, so it turns out these kinds of statements are very answerable in the context of Hodge theory, and this is something that's been worked out at least over the past sort of 10 years, and is, in some sense, this question of actionable theorems has almost completely been worked out. Let me just give you sort of a list of settings in which you can conclude in that setup that the projection of U must acquire more Hodge classes. So in other words, the sort of answer I'm giving you to this question, in a Hodge theoretic situation, if I have an intersection with some algebraic locus that's unexpectedly big, then there must be more Hodge classes that are accounting for that atypical. Okay, so this can be done in all of the following cases. So going back to work with Bakker, and Zimmerman, if you take as your Y to be a Shimura variety, for instance, moduli space of abelian variety, and take M hat to be the compact dual of the universal cover, which universal cover is a bounded symmetric domain, so take the compact dual to be M hat, then you can prove this theorem. Bakker and Zimmerman proved that an atypical intersection only happens when U is in a Shimura subvariety. In other words, when it acquires more Hodge classes. I'll go a little bit fast to this because I actually want to get to the examples where it's a little more clear what the difference between each of these contexts. Okay, so Zimmerman and myself then sort of upgraded this to arbitrary pure variations of Hodge structures, for instance, coming from smooth projective families. And once again, you take as your M hat the moduli space of Hodge structures. So more precisely, you take it to be the sort of flag variety parametrizing Hodge projections. Then this was upgraded by a student of Jacobs, Chu, and also independently by Gao and Klingler, who did this for admissible variations of mixed Hodge structures. So I haven't really mentioned mixed Hodge structures, but due to work of Deline, any smooth projective family has pure Hodge structures on its cohomology groups. Any complex algebraic variety has a mixed Hodge structure on any of the cohomology groups. Okay, so these are sort of Hodge theoretic data that arise when you both allow singularities and non-compactness. And finally, and this is sort of recent work with the Zimmerman, this is sort of the kind of meta theorem that take your Y to just be the total space of the algebraic flat vector bundle underlying the variation, and then hat the sort of universal flat bundle. Okay, so like I said, I sort of didn't expect you to fully digest this slide because I'm going to use the next slide to sort of tell you how these different contexts behave with respect to our family of elliptic curves. So what are the sorts of statements that we're actually extracting? Well, consider n different algebraic families of elliptic curves, E1 through En, and consider, give ourselves a section for each one, and also give ourselves an algebraic one form on each one. Okay? So the kind of transcendent statement that the first kind of theorem gives you is if you consider these taus, these ratios of the period. So what now we can identify what this tau is. This tau is really just a flag variety coordinate of the Hodge filtration, right? I mean, this tau parameter is telling you what the line given by H10 is inside the Hodge structure without telling you anything individually about these two periods. Okay? So the concrete statement here is that if I take all these tau i's, there's n of them, so you would, assume that they are algebraically independent. If they're sort of not transcendentally algebraically independent, by a factor of k, so in other words, if there's sort of k algebraic relations among them, along a locus U that has codimensions smaller than k, okay, so you would expect there to be k algebraic relations between these things on a locus of codimension k. If we're saying it's strictly less than, that's a strictly bigger locus where you have those algebraic relations. Then the conclusion is we must have some extra geometry going on. And the conclusion is that either some of the EIs are isogynous or one of the patches is isotrivial. I should have said over U. Okay, we're only including something over U. So that's sort of the world that this first batch of theorems tells you. What does the mixed version tell you? Well, now I'm going to use the section. If I take a relative homology cycle from 0 to the point S, right? So in other words, before I was looking at the elliptic curve and I was taking integrals of algebraic forms with respect to these two cycles. But now if I take some point, I always have a 0 point. If I take some point S, I can choose some additional path gamma from 0 to S. And in the mixed setup, I have access to the ratios of these relative periods. Okay? So now I have two n numbers. I have my tau i's, and I have these ratios. And once again, if they satisfy k algebraic relations along a subset of codimension smaller than k, then either one of these two extra geometries must be happening over U, or some of the SIs must be torsion. Okay, and finally, the sort of third setup is now where I have access to all three n of these functions. So now I don't take ratios at all. I just literally take the integrals of my algebraic forms with respect to the basis of first homology and the relative homology. And if they satisfy k algebraic relations along a locus that is codimension smaller than k, then one of these possibilities must be. Okay, so in each case, you are able to sort of explain in this case geometrically, but in general, Hodge theoretically, where additional unexpected algebraic dependence on periods is occurring. Yes, any questions? This is sort of this is a much more understandable slide than the previous slide. So pause for a second. Okay, so I do want to say a few words about applications. I'm not going to say so much about the proofs theorems. I do want to say something about applications because somehow the way I motivated considering these functional transcendence analogs was that they were easier than the transcendent statements about numbers. That's never a good way to motivate questions. Well, the other motivation is that actually these functional transcendence statements naturally show up in a variety of places. Not surprisingly, they show up within Hodge theory itself. Perhaps more surprisingly, they show up in arithmetic applications. This is, I want to say a little bit about work of Lawrence, Banketish, and Hast on using sort of Hodge theory very much over C to deduce actual arithmetic consequences. Okay, so I apologize for people. This is going to be slightly for, maybe not for the experts, but for people who are a little more acquainted with algebraic geometry. So let's fix some moduli space Y of smooth projective varieties. So you can think of Y as being the moduli space of genus G curves, or the moduli space of abelian varieties, or the moduli space of one of the other sort of examples I gave, sort of Calabi-Yamaha holds a particular definition. And once again, let M hat be the flag variety of Hodge filtrations that arise on some cohomology group of the varieties parameterized by Y. Okay? And let's assume that the period map you get has finite fibers, meaning that you can essentially completely detect, you can detect all deformations of your variety in terms of deformations of the Hodge. In other words, we're basically assuming that the variety can essentially be recovered from its Hodge state. Okay, so we can ask the question, all right, let K be a number field, and S a finite set of primes. When is the set of S integer points of Y finite? So geometrically, this is asking when are there finitely many of the varieties parameterized by Y defined over K, which have good reduction outside of S. Okay, so this is a sort of type of statement known as a Shaffer-Hibich type conjecture for the varieties parameterized by Y. And Lawrence and Banketish give a pretty robust framework to try to, like I said, use the fact that over C, Hodge theoretically, we can sort of, you know, how to say, the variety is determined by its Hodge structure to sort of manufacture finiteness of S integer points. And the basic yoga of this argument is encapsulated by this diagram. So again, I'm going to go very fast over this. But the sort of takeaway point for the non-algebraic geometers is that if I'm starting with a variety X, which is defined over a number field, I can still take the sort of algebraic Durand cohomology and in some sense the singular cohomology, but these two groups acquire some additional arithmetic structures that make them much richer. Okay, so this Durand cohomology group that we've already discussed, if I look at a variety that's defined over, so this is really the chaotic completion of K. If I look at let's just say it's QP. If I look at the Durand cohomology over QP, in fact, we get a filtration, which we already knew, but we get some additional structure, which is basically a lift of Frobenius from special time. Okay, so you don't know what that means, just forget about it. We just get some extra structure. And likewise, the sort of replacement for singular cohomologies, in some sense, the Tal cohomology, which is a Galois representation. Okay, and chaotic Hodge theory allows us to sort of, in some cases, go back and forth between these two different habitats. Okay, so what do we want to show? Well, we want to show this is finite. Okay, so using Galois representation, you can show the image here is finite. Okay, and what you therefore want in order to show that this is finite is to show that the fibers are finite. Now, by assumption, we know that the fibers of this map are finite. Okay, so it remains to understand how, and this is sort of the key point, if we want to conclude that the fibers of this map are finite, which would then imply that the fibers of this map are finite, we need to look at how the image of this map intersects the sort of image under this forgetful map of isomorphism classes. Guys, I said that slightly out of order, so let me go back. So this is just parameterizing the Hodge filtration. This map is forgetting this extra feed stuff. Okay, so the notion of isomorphism up here sort of respects V and the filtration, and all we get from this map is something that's defined up to isomorphism. Okay, so now over C, the notion of isomorphism is pretty rigid because we have to preserve the Z lattice. But here, there can in fact be continuous families of automorphisms of a filtered phi module. Okay, so a locus of filtered phi modules that are isomorphic can easily project down to a positive dimensional thing down here. So having finite fibers here will not necessarily mean you have finite fibers here. You somehow want to say that the images here intersect those images of isomorphism classes finitely. Okay. And so the important points are that the images of these isomorphism classes are algebraic subvarieties, right? These are just the loci of filtrations, which, how to say, admit an endomorphism that commutes with phi. And therefore, we're reduced to a transcendence question. We want to know when the image of P intersects a certain algebraic variety here, atypically. Okay? And then the second key point of this argument is that, well, a priori, the transcendence statements we've talked about are over C, so they don't really say anything about what's happening for this p-adic analytic map. But in fact, they do, because the Picard-Fuchs equation that we wrote down before is defined over Q. We can solve it both complex analytically and p-adic analytically. And if one of those two solutions satisfies an algebraic equation, the other must. Because in some sense, solution to this satisfying an algebraic equation can be checked for the formal power series. So it makes no difference whether we check it p-adic analytically or not. So indeed, you can use the transcendence over C to say something about how this map intersects the sort of isomorphism, the isomorphic filtration, the isomorphic filtration loci, and thus conclude something about the finiteness of the fibers of this p-adic period map. Okay, so again, I apologize. That's sort of going through it very quickly. That's the basic idea. This allowed Lawrence and Engeltech to sort of reprove Mordell. In other words, showing that Shafarevich is true for curves, or more specifically, that genus G bigger than or equal to 2 curves have finite points. And that, of course, was known due to a result of faultings. The sort of new thing that they get is that you can also apply this principle to you can try to apply it to anything that is determined by a Hodge structure. So for instance, they apply it to hypersurfaces. And what they conclude is a sort of generic version of Shafarevich. They prove that in the moduli space of hypersurfaces of big enough degree, outside of some proper algebraic locus, you only have finite distance. Okay, anyway, that was maybe too long to spend. So in the last few minutes, I promised I should also say, I didn't mention the work of Haas. The work of Haas, so this learned the work of Lawrence and Engeltech was sort of earlier. It only used the sort of pure, the transcendence of pure period maps. Haas then showed how to use mixed ensemble to sort of upgrade the Chauvet-King method to higher dimensional varieties. Okay, so in the last few minutes, I want to say something about some technique that's used in some of these proofs. And there's sort of a lot of techniques that are used. A lot of them are sort of related to traditional Hodge theory. Something that has shown up more recently and has only grown in importance is the appearance of what are called O-minimal structures. Okay, let me say a few words about that. So once again, we have this picture where we fix a lattice, maybe with some auxiliary data, and we consider M to be the moduli space of maybe mixed Hodge structures on B, but we're talking about pure Hodge structures on B. And this sits inside an algebraic variety, which is parameterizing Hodge filtrations. Okay, so certain Hodge filtrations come from actual Hodge structures. So this is sort of a semi-algebraic subset here, but no, it's not everything. Okay, so the best possible scenario you could be in is if the space of Hodge structures modulo integral isomorphism has an algebraic structure, and that is the case for Shimura varieties. For instance, the modular curve is the upper half plane modulo SO2C. Okay, so sometimes this indeed does have an algebraic structure, and then you have many techniques at your disposal. This is unfortunately almost never the case. So the sort of Shimura varieties that show up in this level of generality are few and far between. But this space of Hodge structures modulo integral isomorphism doesn't fully get bad. So it's no longer an algebraic variety, but it still maintains some sort of shadow of the niceness properties that algebraic varieties do. And this is what the O minimal structure is encapsulating. So here's an example theorem that is getting at this. This is not algebraic, but it does naturally have a semi-algebraic structure. Concretely, what I mean by that is it has a finite atlas by real semi-algebraic sets in some Rn, and it's glued together by semi-algebraic functions. Okay, that's kind of like having an algebraic structure. It's not quite, but it's better than some random complex manifold might have. And if we now consider period maps, in other words, the maps that we get from, say, a family of varieties by associating to a point the Hodge structure of that point, it is not going to be the case that this map is semi-algebraic, right? So I mean, S is an algebraic variety, and therefore has a natural semi-algebraic structure. But it won't be the case that the sort of map, when I restrict to semi-algebraic atlases, looks semi-algebraic. That's just way too restricted. What is true is that these functions are definable in the O minimal structure. And so this clock, which is the correct clock? This clock or my phone? Do I have 0 minutes or 3 minutes?
It's 4.
Okay, it's 4. Okay, so let me just end then by saying sort of what, let me just add this last line, which says that O minimal structures, in some sense, are classes of sets in Rn which allow for more functions, but still have all the nice properties that semi-algebraic. And there's a well-developed theory here. This sort of concept originated in the 80s and has been thought about quite a bit by model theorists. But the important point here is that basically all Hodge theoretic constructions can be done within an O minimal structure. So all of the functions we end up using in Hodge theory have these strong finiteness properties that semi-algebraic sets also have. And this leads to sort of a host of algebraicity phenomena. Anyway, let me stop there.
Any questions?
I actually have both a comment and a question. So the comment is also partly people who are in my class. I can't quite tell how, because we talked exactly about your example of Legendre family with the curves. And so these ratios are more or less quite related to elliptic integrals. And so one comment to make is when you first study elliptic integrals, you end up with these bizarre relations between these different ellipticals, where you have this parameter lambda and a parameter involving some algebraic function. And then you sort of explain them by isogenies in the end. And kind of one consequence, I think, of this is that that's the only way you can have algebraic relationships between elliptic integrals, is they're not just isogenies explain them, but that's really the only way that they can have.
Absolutely, yeah. I mean, I would say the only way to have sort of atypical relations. But yes, I mean, that's, yeah, that's right.
My actual question is in these M on GZ, which are just on the previous page, so these are they still have some complex structure. I mean, can you ever give bounds on? I mean, they could still have algebraic varieties inside them.
Yes.
Can you say anything about like the closure? Like, could you rule out, for example, I'm not quite sure what topology I want to use, that algebraic varieties being more or less dense?
I see. Here's kind of an answer to that question, but not really. So if you take sort of this M hat, the well-behaved, so you have M sitting inside the M check, and the sort of well-behaved quotient is, I was writing down M check modulo GZ, but sort of M modulo GZ is this sort of nice complex manifold.
Yeah.
That's like the actual Hodge structure is modulo integrals. And we know in some sense infinitesimally algebraic varieties are sparse in there because of Griffith's transversality, right? Something we can, so first of all, something we proved a while ago is that images of period maps are algebraic. So you indeed have all these algebraic subvarieties of this M mod GC arising from any variation of Hodge structure we have. We can prove using sort of deformation theory that in fact there are only countably many of these algebraic varieties inside any particular M mod GC. And other than those few facts, I would say it's not really known how dense the algebraic varieties are inside of there. I mean, no, it's not everything by Griffith's transversality. I mean, I'd say it's not infinitesimally everything. But yeah, there's no real good answer to sort of how.
So, but do you feel, and this is more a philosophical question, do you have any insight from these things whether you would have guesses, for example, that like in situations where you have countable things, like maybe
No, sure.
Could it actually be finite in some settings, or could it actually be not be infinite?
Well, I would suspect you can come up with some that are.
Or at least, do you think that there could be a philosophy that could predict what happens?
I mean, how to say you could produce an example with no Griffith's transverse direction, in which case there would be none. So
I mean, the most classic avatar of this question, even just for points, is you have these rigid Calabi outs.
Yes.
And this question, well, these are points.
yes.
Like, are there finally many of them or infinitely many of them?
Yeah, right.
And,
So yes,
Does this shed any light at all?
this technology will not give you will not allow you to get some handle on sort of questions. Well, I mean, how to say, there's sort of two questions within that question. There's a question of sort of effectivity of Hodge structures, like if you actually realize them in geometry. That this certainly doesn't touch on. The question of whether you can bound, something that is possible, it's at least in the direction, is maybe you can try to understand sort of algebraic subvarieties of these M mod GC of like bounded volume or something like that. And you might even be able to try to get some like finiteness of components, sort of whatever, do a D space. In other words, there should in some sense be a Hilbert scheme of subvarieties arising as images of period maps. See? And you could hope to prove some boundedness statement for bounded volume. But in terms of once you start looking at all of them, I don't really have a feeling for. I would expect they're pretty sparse, but then again, I wouldn't be surprised if in some examples you have quite a few. I don't know if that's the best answer to your question.
Any other questions? Okay, so let's thank Ben again.